Welcome to part 2 of our lecture on dimensionality reduction. I think you'll find these methods as interesting as principal component analysis. They really will add to your toolbox in allowing you to perform dimensionality reduction on different kinds of data, to perform different kinds of analysis, and so on. So we'll talk about feature selection first, then factor analysis, and lastly linear discriminant analysis. So let's talk about feature selection. As you can imagine, feature selection is referred to by many names. I've mentioned feature elimination, there's also variable selection, attribute selection, etc. The principal idea is to have a process for selecting a subset of features that will simplify models, produce shorter training times, avoid the curse of dimensionality, and enhance generalization by reducing overfitting. Now, there are a number of ways to conduct feature selection. For example, there's the old trial and error method in which possible subsets of features are tested to see which minimizes the error rate. Before we get into more specific procedures, let's review some of the concepts I've just mentioned. Perhaps the greatest challenge in machine learning right now, particularly in deep learning, is optimization or training. As it turns out, optimization and training really are two sides of the same coin. That is, in machine learning, we rely on training our algorithms in order to increase the accuracy of the results they produce. But this is also optimization, because the purpose of optimization is to minimize the error rate. So it's often true that we translate the training challenge by focusing training on optimization. This is then an exercise in minimizing errors. So that would have to do, for example, with the objective function if you're using gradient descent. Unfortunately, this often results in exactly the opposite effect on generalization, because depending on how you do it, it often results in overfitting. And remember that overfitting is due to a model that is too rigid or too complex, and this is typically because it has been overtrained. They applied too much optimization. I mention all this to help you put all these pieces together, because it doesn't matter what the algorithm is, whether it is for classification or regression or whatever. The trade-offs in training, optimization, and errors will really be the same. There are basically three categories of algorithms used for feature selection. There are wrappers, filters, and embedded. Each subset of features is evaluated as a whole by these algorithms. Wrapper algorithms search through the space of possible features. Evaluation involves running a model on each subset of features. Wrappers are computationally expensive and have the potential of overfitting. Filters are similar to wrappers, except that a filter is applied to each subset of features. Embedded algorithms are actually embedded in specific models. Because there are several goals for feature selection, for example, you might want to optimize your runtime. You might want to reduce your error rate. There are many goals for feature selection. So it can be difficult to establish the criterion for selecting feature subsets. Some algorithms include a measure of accuracy penalized by the number of features selected for the subset. Let's look at some examples. This particular slide shows feature selection as a process that removes redundant, having a little bit of computer trouble here, hold on, that removes redundant features. This meets several of the goals of feature selection. However, as was the case with PCA, you have to be careful in applying this method. One way of removing redundant features is to remove features that are highly correlated. For example, if attributes have an absolute correlation of 0.75, and I use the word absolute because that can be plus or minus 0.75, or higher, you could consider removing one of them. Here's an example using the Pima Indians diabetes data set. This data set is in the machine learning or ML bench package. So if you haven't already installed that, you'll need to install it, and this of course is in R. We used the carrot package in the PCA example before. We'll use it again to do feature selection. Carrot uses a wrapper method based on recursive feature elimination, genetic algorithms, and simulated annealing. The genetic algorithms are used to determine which subset of features to include based on root mean square error or classification accuracy. So remember, mean square error is the, industry standard for determining which would be the preferred model. Simulated annealing is a global search method that runs through possible perturbations in order to find a best solution. In the context of feature selection, the best solution is stored as a binary vector describing the best feature subset. I've included the website that I got this example from on this slide. The website suggests that the highest correlated variables are age and pregnant, so age could be removed or pregnant could be removed. However, remember that age itself is correlated with diabetes. That means, what I'm talking about is that when people age, many or probably most people will develop diabetes as they age. So I'm not sure that it's a good idea to remove the variable age. And pregnant, it's also sort of the same thing. Many pregnant women do develop diabetes as well. And it doesn't meet the proposed 0.75 cutoff, as you can see from the slide. So again, care should be taken in applying this method. The carrot package in R is described as miscellaneous functions for training and plotting classification and regression models. The RFE command, where RFE stands for recursive feature elimination, executes an algorithm that makes a simple backwards selection. So you've been or gotten familiarized with backwards selection from our course 510. We'll look at an example using the blood-brain data set. Now, we're going to use the blood-brain data set in assignment 7, but we're going to use it in a different way. This way is, I think, more understandable. So once you get through this example using it, then I think you'll be able to use the bigger full data set more comfortably. The blood-brain data set was developed to predict the log of the ratio of the concentration of a compound in the brain and the concentration in the blood. So there's a barrier between the blood circulating in your body and what's the blood circulating in your brain. And this barrier is important. And so we're looking at compounds and determining the ratio of the concentration of the compound in the brain and in the blood. You can read more about this data set in the documentation for the carrot package or in the corresponding journal article, A Recursive Partitioning Model for Blood-Brain Barrier Permeation by Menti and Lombardo. There's another article, Qualitative Prediction of Blood-Brain Barrier Permeability on a Large and Refined Data Set by Mühlbacher et al., that describes some of the variables and functions used to evaluate the blood-brain barrier permeability. Now, I'm going to warn you that this particular example took quite a bit of time to run on my computer, which is pretty fast, and it's going to take a lot longer to run the steps in assignment 7. There are apparently 208 compounds that were experimentally evaluated with 134 descriptors for each compound. So you see the matrix of variables for compounds gets bigger and bigger. In addition, there were 3 sets of molecular descriptors used. So this is, this is the small data set. This is one that has been cut down. The one in assignment 7, the full data set, is actually much bigger than this. And a second note to make is that I'll also say that I really know very little about medicine, the medical practice in this area. So I would have to take whatever the program returns at face value. I could not take the results and say, no, that doesn't look quite right. And so this is a case where you want to get a subject matter expert involved, and as early as possible, so that as you're running the analysis and you're getting your preliminary results from exploratory data analysis, and you're going through and you're testing different subsets of features, that you've got somebody who knows this area and can tell you if you're doing the right thing or not. There is a significantly more detailed analysis at, let's see, I thought I put it on this slide, but I don't see it on this slide. Is it on the one before? No. Okay, if you're interested in getting this more detailed analysis, it's from our Forge, and it's one of their projects, and it falls under the carrot package. Send me an email to mhamner@mcdaniel.edu, mhamner@mcdaniel.edu, and I'll be glad to send you the URL for this particular article and analysis. On this particular slide, I've printed out the results of the analysis using carrot. And here you can see the top 5 variables out of all variables. They were variable number 2, 5, 10, 20, and 71. And those variables happen to be, and I had to look them up, FPSA3, TCSA, PRX, most positive charge, and TCPA. So I have no idea what these are. I can provide you, again, if you email me, a copy of Menti et al.'s paper and to review it to learn more about what these variables are. Now you can see the same sort of information that we were getting from our other analyses. You can see that we've got root mean square error, we've got R squared, we've got all of the different measures for determining the performance of a model. But I don't see here information that I could use as a layman to determine that these results are the best results. So get that subject matter expert engaged early on so you can tell that you're doing the right thing. Okay, so let's move on and talk about factor analysis. As I said before, this is actually quite different than either PCA or feature selection. Factor analysis was developed nearly 100 years ago by another very famous statistician, mathematician, Charles Spearman, who also developed the Spearman's rank correlation coefficient. He was actually an English psychologist who was also known for his work in statistics. He developed a concept about human intelligence that he saw as an underlying invariant factor, which included mathematical skill, vocabulary, other verbal skills, artistic skills, logical reasoning ability, etc. Today, the College Board Testing Service, up until I guess not very long ago, operated on the concept that there are at least 3 important factors for intelligence. That is verbal, mathematical, and logical. Now I know that there has been many questions about standardized exams, and particularly for the College Board Testing Service, so I'm not quite sure that they're still following this same logic and using the same concepts, but for a long time they did. Factor analysis is useful in examining the variable relationships within complex concepts or factors within areas, disciplines like socioeconomic status, dietary patterns, or psychological scales. It collapses a number of variables down into interpretable underlying factors. In other words, a major goal of factor analysis is to understand underlying causes. Factor analysis has competition from other methods of analysis, for example, clustering, and we'll use clustering in the unsupervised methods. Factor analysis is applied to the correlation matrix. However, other methods such as clustering can be tied to virtually any measure of similarity, and because we'll have to be able to measure some distance. What do we mean by a factor? In general, a factor is a latent variable. That is one that cannot be directly observed. These latent variables arise from multiple observed variables that have similar patterns of response because of their relationship through a latent variable. In many ways, PCA and FA may seem to be the same, but they are not. Both are data reduction techniques in the sense that they both reduce the number of variables in a data set. They both look at the same and are run about the same. That is, they process and they go through extraction, interpretation, rotation, selecting factors or components, etc. But PCA is a linear combination of variables into components, like PC1, PC2. Factor analysis is a model of the measurement of a latent variable. Another definition of factor analysis from the psychology department at Stanford says that a factor in factor analysis is said to exist when the various indicators, and you can interpret indicators as independent variables in a matrix X sub J of the supposedly latent construct or variable cohere. That is, they hang together. These latent constructs are coherent. They hang together. Let's look at an example from this psychology department at Stanford and how we represent self. Self being ourselves. Should be interesting. A stated goal of this analysis is to determine how many latent factors, K, so we're using K again for the number of something, in this case latent factors, how many of them account for most of the variation among the M observed trains or variables. Another goal is to find which trains or variables define each factor and hence what labels we should give each factor. So again, I think this should be pretty interesting. So I'll go through steps in the process. And step one is, as usual, we start by loading the data and looking at the data. And I've summarized some of it on this slide. So you can see that there are quite a number of variables. The data looks to be integer, numeric data. We have down here, we can see that it's set up in a data frame of 240 observations of 32 variables. And so when you do the str command, the structure command for the data frame, it gives you each of the variables and several of them from the beginning of the data set. So step two is to look at the data in terms of correlation. So what I've done here is created a correlation heat map. Based on this correlation plot, there appears to be some underlying structure in the data. For example, there appears to be subclusters that hang together. One example would be talkative, outgoing, and sociable, which are negatively related to shy, quiet, and withdrawn. So at this point, I need to provide you with some technical definitions so that when we're going through this process, you can understand what the steps in the process are talking about. So a factor is an underlying or latent construct that causes the observed variables to a greater or lesser extent. So I put causes in quotation marks because I think causes in this case means effects. Mathematically, a factor is estimated by a linear combination of observed variables. Now there's factor loadings, and factor loadings are the degree to which the variable is driven or caused by the factor, akin to the size of the path coefficient in a causal diagram. Okay, another term that you need to know, communality of a variable, communality, communal, I can't say it, communality, the extent to which the variable across subjects in a variable is explained by the set of factors extracted in the factor analysis. Uniqueness is just 1 minus communality. The next term, variance accounted for by a factor, and that's the amount of common variance for a set of observed variables. The term factor score coefficients over factor weights, it says that it's defined as a factor that's a linear combination of observed variables. It's the set of weights for each factor given the factor score coefficients for that factor. So I think these terms will make more sense when we're actually using them in the process. So the factor score of a person's factor score is a specific linear combination of that person's observed scores on all variables. Now, remember that I said that feature selection was the only method that we were going to use that didn't rely on eigendecomposition. So a term for factor analysis is eigenvalue. The kth eigenvalue is equal to the variance accounted for by the kth most important factor. They are used to compute the percent variance accounted for by a factor and the cumulative percent variance accounted for by the first n factors. So it means basically the same thing that it meant in PCA. The next term, interpretation and rotation of factors. Perhaps the most exciting part of exploratory factor analysis is the choice of theoretically interesting labels for the extracted factors. This is done, in part, by noting which variables have high loadings on a factor and noting also the sign of these loadings. Often the unrotated factors, which are usually the principal components, or PCs, are more difficult to interpret than the rotated factors. That is, rotation is a technique that is used to improve the interpretability of factors. And we're going to see the effect of rotation in just a minute or two. Note that the definition and interpretation of principal components, PCs, is not affected by how many PCs are extracted. If M PCs are extracted, and these M PCs are then rotated to define M rotated factors, the M rotated factors explain exactly the same amount of variance as do the M PCs, their principal components. The interpretation of, say, the first rotated factor might depend on how many factors are extracted. Okay, so going back, I want to repeat what step 2 was before we got into the definition of all these terms. We were looking at the data in terms of correlation, and we were looking for underlying structures in the data, things, variables, subclusters that hang together. And we noticed that talkative, outgoing, and sociable are negatively related to shy, quiet, and withdrawn. So you can see here in this heat map where you've got red subclusters and some blue subclusters, and the red subclusters are on both sides of the diagonal line. So you've got some relationships there that are going to be pretty interesting. Okay, step 3. Step 3 is to standardize the variables. It's pretty straightforward. Step 4, and in this particular package and the way that we're going through this, we're going to use the factanal, F-A-C-T-A-N-A-L command to begin the factor analysis. We set the number of factors to 10. In this case, we set rotation to none and consider the resulting loadings. If you look at the bottom of this slide, at the sums of squared loadings, SS loadings. These are the eigenvalues. That is, these represent the variance in all the variables which is accounted for by that factor. As did PCA, factor analysis uses the Kaiser rule, which says that a factor is important if the value of its eigenvalue is greater than 1. So in this case, it appears that factors 1 through 6 are important. So if you actually went through and you added up the values under factor 1, you would come up with 6.706, which is the SS loadings. Like PCA, the factor analysis provides a linear combination of the variables per factor. And the proportion of the variance in this case was 21% for the factor 1. I'm not an expert in factor analysis, so I don't know if that's good. Again, the SS loadings is what the Kaiser criteria relies on. So any SS loading above 1, we're going to include. So on this slide are the computations to evaluate the proportion of the variance explained by the first factor. As I said before, from the SS loadings, the value 6.706 is divided by the number of variables to get the proportion of the variance, which then is about 21%. So that's, straightforward. In addition, we can look at the uniqueness of each variable. Remember that uniqueness, the term, is equal to 1 minus communality, where communality is the SS factor loadings for all factors for a given variable. If all factors jointly explain a large percentage of the variance in a given variable, then that variable has high communality and correspondingly low uniqueness. Given the table of values for these variables, the computations for the uniqueness of the variable distant are shown on this slide. The uniqueness of distant is found to be 0.4155 and so on. In addition, we can visualize these variables in 2D space by plotting factor 1 against factor 2, and that's what the figure is shown on this slide. You can see when we move along the axes for the factors, the variables that hang together. So you can see in the upper right corner, quiet, shy, withdrawn, distance, and in the lower corner, the lower left-hand corner, sociable, outgoing, and talkative, which are the opposite of quiet, shy, etc. So it seems to be that factor analysis is providing some good information. The variables that are similar are hanging together. They are coherent. The next thing that we're going to do is we're going to rotate these factors and look at the results. Rotating the factors results in each variable loading more heavily on a single factor and less on other factors, making the interpretation of the factors easier. Varimax rotation is the most common type of rotation, and it's also the default rotation in Factinal. A varimax rotation is typically used to simplify the expression of a particular subspace in terms of just a few major items, a few factors. Varimax rotation maintains the actual coordinate system while rotating the orthogonal basis in order to align with those coordinates. Those are mathematical terms, the basis, etc. Within the rotation, you can see that the SS loadings have changed. To me, they seem a bit more evenly distributed, and now factors 1 through 7 are greater than 1. So we've picked up another factor as important because it's greater than 1. So on this slide, I've got the corresponding plot of factor 1 and 2 after the rotation. Remember that distant, withdrawn, quiet, shy, as opposed to outgoing, talkative, and sociable were in opposite corners before. Now you can see that within factor 2, they're at opposite ends of the scale for factor 2. Also, you can see for factor 1, hardworking, perseverant, disciplined, responsible, as opposed to careless, disorganized, lax, lazy, giving up. You can see that this seems to actually be working pretty well. Variables that should be together, hang together, are coherent for a factor seem to be that way. So I put circles around the variables at the extremes of factor 1 and 2 just to make it more visible, the change. We see variables sociable and shy load heavily on factor 1. Variables like hard work, responsibility, and negatively lazy load heavily on factor 2. There's one more thing we can do in this program. We can create composite variables ourselves. If we reduce the number of variables in our data set, our algorithms could run faster, and our models might be more robust, etc. So let's take a look at combining variables down to a total of 5. I've got the R code on this slide along with the resulting factors and loadings. I have to warn you that this is and can be a bit controversial because you're making subjective decisions sometimes in which variables to include in a particular factor. If we plot this up after combining the variables, the 5 we have left are shy, outgoing, hardworking, anxious, and friendly. On this plot, you can see that friendly, anxious, and shy are at the extremes of factor 2, but they vary across factor 1, where before after we had rotated factors, heavily loaded factors were along the axes of factors. In this case, outgoing and shy are at the extremes of factor 1, but again, there's some component of factor 2 in those factors as well as heavily loaded factor 1. So to summarize, factor analysis is a method for modeling observed variables in terms of underlying unobservable latent factors. Let me repeat that. To summarize, factor analysis is a method for modeling observed variables in terms of underlying unobserved latent factors. Factors are typically broad concepts or constructs. If you've done any kind of analysis in sociology, psychology, any of the soft sciences, you will have come across what a construct is and understand that. Factor analysis, while widely used, is still quite controversial due to the subjective nature of rolling up variables into latent factors. things, latent factors are things that cannot be observed and measured. So there's a great deal of interpretation that occurs in factor analysis, and that results in some oftentimes pretty heated debates. Ideally, in factor analysis, each variable should make the most of its contribution to one factor and less to all other factors. Although if you look at this, you've got quite a combination of factor 1 and factor 2 in these factors. In situations where this isn't true, rotations can be made to essentially re-weight the factors so that the variables more closely align with one factor. So our last method is linear discriminant analysis, or LDA. LDA is a method used to find linear combinations of variables that characterize or separate two or more classes of objects or events. So when we do clustering, we're trying to separate classes of objects in clusters. When we do classification, we're trying to separate clusters or groups of things by their category or their classification. This linear combination can be used for either a linear classifier or for dimensionality reduction. LDA is not the same as PCA, but again it's closely related to PCA and factor analysis in the sense that all are looking at combinations of variables which best explain the data, but explain it in a different way. Again, LDA explicitly seeks to find the difference or differences between classes of data. It does not seek to maintain the variance in the data. It's looking to find the differences between classes of data. LDA seeks to reduce dimensionality while preserving as much of the class discriminatory information as possible. So consider the case of two classes. We want to find a way to discriminate between these classes, and one thing we might consider is the distance between the projected means of both classes. But this isn't really a good discriminator because it doesn't take the standard deviation within classes into account. Ronald Fisher's solution to this problem of not taking the standard deviation within classes into account was to maximize the difference between means as normalized by a measure of the within class variance. This became known as the Fisher linear discriminant, and LDA is a generalization of Fisher's linear discriminant. So let's look at an example. We're going to look at the iris data set again, but instead of doing a principal component analysis on it, we're going to do a linear discriminant analysis on it. So instead of trying to preserve the variance in the data set, we're going to try to look at the separation of what categorizes this data, which is the type of iris, Setosa, Virginica, or versicolor. In this case, we'll use the LDA command from the mass package in R. So to avoid any confusion with anything we've done today, we're going to reload the data and start with the data from the very beginning. We'll use the LDA command to find the prior probabilities. Since we have a 150 observation data set with 50 observations per species, our prior probabilities are a third, a third, and a third. The LDA command has also returned other parameters, for example, the means of each of the 4 features per species. If I had known that this package and command would do that, it would have saved me a lot of work earlier when I was trying to do that. Also, we get this data standardized, that is scaled, and in the form of coefficients of the linear discriminants. And the LDA command has done a singular value decomposition on the data. So we also get the eigenvalues back. And we can use these singular values or eigenvalues to compute the amount of between group variance explained by each linear discriminant. In this case, nearly all the between group variance is explained by the first linear discriminant, which is LD1. LDA forms linear combinations of predictor variables such that the average value of these linear combinations will be as different as possible to facilitate classification. Let me say that again. LDA forms linear combinations of predictor variables or attributes such that the average value of these linear combinations will be as different as possible to facilitate classification. Based on the values of the linear combinations, LDA reports a set of posterior probabilities for every value of classification for each observation, along with the level of the classification variable that the analysis predicted. So on this slide we've used the LDA command again, but this time with CV equals true, to use a leave one out cross-validation and return a named list of components. So you've used cross-validation now and should understand what that's doing. Then we split out half the iris data set for training and use the predict command to classify the remaining half of the iris data set as a test set. So this is a little bit different split. This is a 50-50 split, which is a little, we usually use 80-20 or something like that, 80% for the training and 20% for the test. So this is one way to do it. On the next slide, we'll look at a second way to do it. Using this method, we'll split out a 50 observation training data set from the iris data set and attempt to classify the remaining 100 observations using the LDA and predict commands. The R code is shown on this slide. Essentially, we're using the same commands, but setting up the tables slightly differently. This is to facilitate generating the truth table or confusion matrix as shown on the slide. And it looks like there really are only 2 observations that were misclassified, but that can't be right because Versicolor has 32 and let's see, 32 and 32 is 64 plus 2 is 66. No, that's all of them, plus 34 is 100. So it got all of them. And misclassified 2 observations. Since there's considerable overlap between the Versicolor and the Virginica species, I'm surprised there isn't really more than 2 misclassifications between those. This slide has a shorter version of the R code for both PCA and for the LDA, as well as generating comparison plots. And here are the plot. You can see the reference at the bottom from GitHub. Here are the plots, and it's really interesting to me. They actually look almost like they're mirror images, which seems odd because I would not have thought of these two things which seek to do different things. One preserves variance and the other preserves differences between classes. I would not have expected them to look like mirror images. So that seems a bit odd, but they do. You can see where it splits the setosa out, which is a much smaller in terms of size species than versicolor and virginica, and you can see there's some overlap, although in the linear discriminant analysis it really has done a better case of splitting out the versicolor and the virginica. There's much less overlap between them than there is in the PCA. So in a sense, linear discriminant analysis is closely related to logistic regression analysis in that each attempts to express one categorical dependent variable as a linear combination of other independent variables. However, logistic regression does not assume that the independent variables are normally distributed where linear discriminant analysis does. If the distribution is significantly non-Gaussian, non-normal, the linear discriminant analysis will actually perform badly or very badly. Linear discriminant analysis can be used for dimensionality reduction before classification. This is similar to PCA, except that linear discriminant analysis, or LDA, seeks to preserve as much class information as possible. So we've said that many times now, and that's exactly what the difference is. So we've completed now a discussion of our 4 methods of dimensionality reduction: principal component analysis, feature selection, factor analysis, and linear discriminant analysis. And this actually ends part 2 of that discussion. I hope you've enjoyed these topics. They are important, and I hope you go through these examples and practice this a bit, because this will greatly add to your capability, and it's a good thing to have in your toolbox.